See a full, do you see full screen now?
Full screen, yes, but it's still not presentation. It should be.
Okay, I'll put it in a presentation mode.
No. Yeah, it's full screen.
You see it now, full screen and the presentation mode?
Yeah, fine.
Okay,
Excellent.
so I'm stop sharing and I will join soon.
Okay.
With the presentation.
Hi. Long time no see.
Long time no see. Yes, Professor Bosanac, because we are busy with issues which have nothing to do with space. We are busy now in protecting ourselves, and thank God we have this Iron Dome which takes us as close as possible to space, and providing us a defensive shield.
It is really impressive. It is really impressive. And well, I'm sorry to hear it because it's really totally illogical. I mean, I really don't know what these guys want to do. I mean, I know what their intention is, but I mean, it's not the way to go around. It's just terrible. I hope you go through this without too much of damage and especially loss of lives. And I hope all the best that everything finishes.
Thank you, Professor. You're a good friend. And thank you, Mr. Sarid, for having this webinar or seminar or project with us. This is the second time in 2 weeks that we meet virtually like this. I hope the third time, not only you will bring me some ice cream, but we'll be able to meet in person. But coming back to the topic of today, thank you, Professor Bosanac, for organizing it. I think it is very, very important to bring this topic to the attention of as many Croatian citizens as possible. Because this is a topic which can bring our countries and our societies even closer to have the same challenge in space and to participate in a very unique project called Beresheet 2, Genesis 2, to have a soft landing on the moon by a small country like Israel. Well, China put an object on Mars, but we are not China. We don't have the pretension to be China, but the moon is in our reaching, bearing in mind the past that we were that close to having it. So this seminar, this webinar, which was organized by the Adriatic Aerospace Association and the Embassy, is another step into this direction in bringing young people from Croatia closer to the topic and closer to Israel and closer also to similar high schools in Israel, which have the same idea of reaching out from the daily activities and have big dreams toward outer space. I will stop here with my welcoming remark. I will have to apologize because I will have to leave in 5 minutes since I have to go out of town to something which was not planned, but I must go there. So I will leave all the participants in the good hands of Mr. Sarid and Professor Bosanac. And I wish all of us luck. And our luck or our success will be measured by the number of people from Croatia who will show interest in this Beresheet 2 project, Genesis 2 project, and will be willing to give a hand to implement and to realize this wonderful idea of landing on the moon. You know, in Israel, in the Jewish people, it is all known the following proverb or say or principle: he who does not dream, he is not a realist. So I think it's a nice place for dreamer, and dreams in Israel usually are coming true. So good luck to everyone. Thank you for the participation. And as I said, I will have to leave you in a few minutes. Don't take it personally. Thank you and shalom.
Thank you.
Okay,
Thank you, Mr.
Shimon.
Ambassador.
Yeah, well, just few words. That's precisely what is my also idea of being realistic, to dream about projects. And that is one of the main reasons why I contacted Shimon, and then to that a project of Beresheet should be presented here, that to see, to help also to realize the dream that SpaceIL and Israelis have reaching the moon. What's fantastic about the Beresheet project is that it is done by an organization very similar to our organization. In other words, non-government organization. It only shows that you can destroy the monopoly of the big things, or the big entities like NASA or ESA or something Chinese, to have the monopoly of getting to moon. Well, Mars is a little bit further on. That's a little bit more difficult, but at least moon. So here I'm looking very much forward to see how we can help and participate in this project. And I give now the words to General Sarid to tell us more about Beresheet and see how can we get involved in this. Okay.
Okay. Thank you, Professor, for the introduction. My lecture or presentation today will have like 3 chapters. In the first chapter, I'll talk about the Beresheet 1 project that's already behind us, and about SpaceIL for a few moments. And then I'll continue with the Beresheet 2 plan for the next project of Beresheet. Actually, already started in the design phase. And my third chapter will talk about challenges, technology challenges in space, looking from the perspective of Beresheet 2. And it will be a little bit technical, but I believe that most of the people here that are in the space business are some sort of technical people. So I hope that you find interest also in this chapter. And we will allow like 10-15 minutes for question at the end of it. And altogether will take approximately 1 hour, 60 minutes. So let's start. I'll put my presentation. Now, do you see my presentation in a full screen presentation?
Yes, it's visible. Yeah.
Yeah, okay, very good. So this photo that you see here is original photo taken by Beresheet 1 on April 11th, 2018, about 32 years ago, when it was in the final descent to the moon surface. Sorry. Now, when we talk about SpaceIL, we have to realize that our mission system, our mission statement is to inspire the next generation of scientists, engineers, and dreamers. And we do this goal or this mission statement by the execution of highly challenging and scientific and educational space mission in deep space. So actually, we're not a company that is building commercially a spacecraft. All we do is to make this kind of project in order to inspire a generation of children and students between the age of 5 to 25 and to make them learn the STEM education, science, technology, engineering, mathematics. And this is what we do. And we do it while trying to position Israel as a leading country in the international space community. SpaceIL was founded in 2011 by 3 young Israeli engineers. They were responding to the Google X Prize competition that promised like $20 million prize for a group, a non-governmental group that will reach to the moon and do some specific mission. About 30 groups from around the world organized to meet this challenge. The only one that survived up to the launch to the moon to do a lunar mission was SpaceIL. It took about 8 years and $100 million to reach to that point of the launch to the moon. And we did it on February 22nd, 2019. About 6 weeks later, we completed successfully the capture by the moon. So we left the gravitation of Earth and captured by the moon gravitation. And about a week later, on April 11th, 2019, we started the landing process. It was initiated in the altitude of about 25 kilometers from the moon surface. About halfway to the moon, 12 kilometers from the moon surface, we had a technical problem that happened to develop to a system problem. And then instead of soft landing, we got hard landing on the moon. It was some kind of disappointment, but it doesn't erase or delete the achievements of Beresheet 1. I have now a 4.5 minutes of video about the story of Beresheet 1 before we move to Beresheet 2.
The story for me started when Yariv Bash, Jonathan Weintraub, and myself met together and started thinking about how we're going to build the first Israeli spacecraft. It started from the Google Lunar X Prize competition, an international competition to land a private spacecraft on the moon. But really quickly, it became something much bigger for us, and the vision to inspire the next generation of scientists and engineers. And this is what we have been doing in the last few years.
The SpaceIL program had tremendous challenges. We were trying to do something that had never been done before. We were doing a private, non-government mission to the moon. We were doing it significantly cheaper than had ever been done before. We were doing a new space mission, not a conventional space mission where you've got thousands of people working on it and costing hundreds of millions of dollars. All of that sounds complex, but when you drill down, it's even more complex than it sounds because we are actually reinventing how you conduct such a program.
From the space community point of view, it was the first non-governmental spacecraft to the moon. It was the first spacecraft with almost no redundancy.
This is an incredible achievement, not just for the nation of Israel, but for all countries and commercial space. And we are proud to have partnered with you.
We had a lot of challenges through the years. It started in the beginning in just understanding how the spacecraft is going to look like. It took us 5 years just to get a design that can actually get to the moon. In parallel, we needed to raise a lot of money, but then also tackle the engineering. And in the engineering project, there were a lot of things, a lot of details that we had to figure out, a lot of things we designed and, again, didn't work.
I joined the project at the beginning of 2018, and the major challenge was to bring the spacecraft to the launch pad on time, on schedule.
With a lot of work and with a lot of help and with the support of the Israeli aerospace industries and the Israeli space agencies and our donors, Maurice Kahn and the Edenson family and many others, we were able to get to that moment with a working spacecraft. But even then, after we launched the spacecraft, there were still a lot of things that didn't work as expected.
Those 7 weeks were very, very challenging for the technical team. They worked relentlessly, day and night, 24/7, with very little sleep. to figure out what the problems were, to come up with very clever solutions to them. In the final stage of the landing, we came across a series of small problems that joined together and ended up in the spacecraft being without the motor on for much too long, and we reached the moon's surface much, much, much faster than we'd ever expected.
We wanted to soft land, but eventually we crash landed. It was a sad moment for everyone, but really quickly we remembered that the bigger impact we tried to create was not on the moon, it was here on Earth.
Even though we landed on the moon much faster than we wanted to, and in too many pieces, it's still a tremendous success because the mission was not to get to the moon. The mission was to get Israel's youngsters, aged 3 to 93, excited about technology, excited about dreaming and making those dreams come true. And this we achieved.
It was very exciting to see how all Israelis and how all the children followed the mission after the launch and before the launch, how they were connected to the mission.
We got much closer to the moon than anyone else had done in the first try. We did it in a way that nobody had thought possible a few years earlier, against very heavy odds. So the mission itself, in my view, was extremely successful, and the outcome was fantastic.
SpaceIL has been working in the last few years to get the next generation of scientists and engineers inspired on STEM education. This is what we are planning to continue doing through the next project, Beresheet 2.
The Beresheet program created a lot of impact within all the people, in which Israel became all of a sudden one of the few countries that dealing with deep space for the first time. And with the generous contribution of Mr. Len Blavatnik, now we are able to move forward with this program. Join us to the moon. So this is the story of Beresheet 1. Just to summarize the achievement of Beresheet 1. So we were the first Israeli spacecraft in deep space. Israel is dealing with space for many years now, but mostly in the LEO and GEO activity, not in this deep space. So we were the first one in Israel to do so. We were the fourth country to touch the moon by a lander, even though it was a hard landing. But we did it after United States, Russia, or Soviet Union, and China. So it was a great honor for us. We were the first non-government organization in the world, not only in Israel, that did a lunar program at low cost, of course. We got a lot of national pride here in Israel in this project. It was like a mini Apollo effect. And we actually put the Israeli flag on the moon. When you see this picture here, it's also a photo taken by Beresheet. You can see the landing leg on the left, and you see the flag of Israel on this plaque, part of the spacecraft, and it's on the moon. We inspired a lot of children, like 1 million children in Israel and another 1 million children abroad, by telling the story of Beresheet and let them participate in the program. And above all, it was a dream that came true in a big way. And this is something that everybody can learn, how to dream big and make it happen. So this is the story of Beresheet 1, and Beresheet 2 begins from our perspective when the Beresheet 1 ended. Even though the mission was not 100% completed in Beresheet 1, we decided to make another journey of Beresheet, and we built the Beresheet 2 building, let's say, on top of Beresheet 1 achievements. And now I have like a 60-second video on Beresheet 2, which is trying to explain the mission of Beresheet 2. to those of you who didn't capture the whole picture here from the video, just repeat on this. As you see here, Beresheet 2 is a system of 3 spacecraft attached together. We have on the middle here, on top on the middle, and the middle here, what we call the mothership or orbiter in our language. And we have 2 other spacecraft, smaller ones. We call them landers. You see it on the left side and the right side of this slide. This package of 3 spacecraft attached together will do all the way to the moon after being launched to space. And after capturing by the moon, the mothership or the orbiter will release the landers to land on the moon. They will be landing on the moon in different locations and different time. And each one of them will carry a different scientific payload, experimental payload, to do some scientific experiment on the moon surface. And after the completion of this stage in the mission, the orbiter or the mothership will continue to orbit the moon for about 2 to 5 years and serve as educational tool or hub in a way that children, students will be able to communicate or to interact with the orbiter and do some work together and have the feeling, a real feeling of touching and spacecraft on a real-time basis that is orbiting the moon. So this is the mission. You can see here a model of the system. On the left side, you can see the mothership with the 2 landers attached to the orbiter. You see it with the folding or folded or retracted landing gears or landing legs. On the right-hand side, you can see the 2 landers with the retracted landing legs and the deployed landing legs. And after the release or deployment of the landers from the orbiter, the landing gears will open up and deployed for the landing. Now, what are the added values of Beresheet 2 compared to Beresheet 1? So first, we are doubling the mission effectiveness. The fact that we have 2 landings at the same mission in 2 different locations on the moon surface makes 2 missions at one sortie. So we are tripling the scientific payloads because we'll have and each component of this system will have scientific equipment. After accomplishment of the mission on the moon, we'll stay with the orbiter continuously orbiting the moon and serving as educational instrument for the school children and students. We are carrying strong educational messages. We are raising the bar, which means that even though we didn't complete 100% the Beresheet 1 mission, we are not afraid to go back and try again. But this time, we go back with a much more challenging mission, inspiring mission. We are taking some risk here, but we are not afraid to do it. So this is the nature of SpaceIL, and this is the spirit that we are trying to create in Israel and abroad. The other message is they are going together. As mentioned before, this program will be open to some international partnership. We'll talk about it later. And we, of course, encourage STEM education to all the children that will be exposed to this program. So we are opening this also for international partnership in various levels. And by doing so, we are positioning also Israel to be some sort of leader to international space community, to those countries that will decide to join us. When we talk about international partnership, we see like two levels of partnership. One of them is the basic level, is to partner with countries that would like to participate in the educational part of the program. And this kind of participation is actually unlimited in terms of how many countries can join and enjoy the fruits of this program. And our idea is that if we are already paying like $100 million for this program, why don't let other children around the world to enjoy it, in addition to the Israeli school children and students? So this is the basic participation. The other level is the for the countries who have already have some space capability and would like to participate in terms of participating in engineering teams or in the production or testing or doing something for the program from the perspective of engineering, manufacturing, testing, and participation in the mission and the payloads. So this will be open only for one or two countries because to manage such a complicated program with too many partners that are involved in the engineering and production is too complicated. So this kind of level of participation is reserved to few countries, preferably two countries that will be part of the engineering process and manufacturing. So this is the issue of the participation. When you look on the world-class achievements that we would like to achieve in this Beresheet 2 program, first of all, the dual lander deployment from one orbiter is something new. Nobody did it already in the world, so probably will be the first one to do it. So this is like a record that we are trying to set in our program. The other achievement on the bottom here will be the smallest landers ever to softly land on the moon. Each lander will weigh like 120 kilograms at the release point. And after landing or in touchdown, the weight will be like 60 kilos after consumption of the propellant or the fuel all the way to the moon. So it will be like 60 kilograms, and we'll have to compress all the technology needed to land on the moon and performing a scientific experiment in 60 kilos. This is a great challenge for us and for everybody, and we are going to do it. And the third challenge that we're trying to achieve in this program, it's not decided yet, but we started to work on it. And the idea is that if we already have 2 landings on the moon, why don't we land the first one on the near side of the moon and the second one on the far side of the moon, that side that nobody on Earth can see ever. So this put another challenge and complication to the program, and we are checking the possibility to make it as a part of our program. And if we do so, we will be the second one to land probably on the far side of the moon. The only one that already did it are the Chinese, like a year and a half ago. And they will be the first one to do like a double mission, land on both sides and the same mission in the world. So we're very excited about it, but we have to check it very carefully and also to implement it. Our educational vision is to create with the orbiter or the mothership like a worldwide space education system based on the orbiter. You can see on this chart on the left-hand side, you see the orbiter circling the moon for about 2 to 5 years. And this orbiter will be connected to a control room in Earth. And this control room will be actually connected to space education centers, to children, schools in different countries. You can see on the right-hand side the flags of the continent of Africa. Specifically in Africa, there are many, many countries. They don't have any space capability, but their children are striving to touch space. So this is like an example how we can leverage this program, but it's not necessarily focused on Africa. It could, many countries can let's say, be part of this educational program and let their children and organizations, space centers, to be part of this education campaign. So we look at it in a big way, and the students or children that will be connected to the orbiter will be able to get data, information, photos, to ask questions, to get answers, and to get information about experiments that will be running on the orbiter. So they'll have a full kind of activity and experience of dealing with space with this orbiter. This is our vision. It's also complicated to, of course, to implement that, but all this program is challenging anyhow. So we believe that we can do it. This is the timeline of the program. We actually officially launched the program on December 9th last year. And now we started the preliminary design phase. And we are aiming to launch our Beresheet 2 spacecraft system in mid-2024. This is very ambitious, but it's doable. This is a photo from the launch ceremony with the President of Israel. Here is in the middle of the picture. You can see this is the Corona time in which everybody was masked. So we have here the Minister of Science and Technology next to the President, and we have few SpaceIL people, and the CEO of Israeli aircraft industry who is partnering with us in this program. On the right-hand side, you can see the first drawing, let's say, of Beresheet 2 system, conceptual design, and you can see the signature here, and the top signature here is the signature of the President of Israel. So it was part of the ceremony. So this is the story of Beresheet 2. We just began this story. And with that, I would like to move to, assuming that you have enough energy to continue, I would like to go to the last chapter of my presentation here today, which is talking about space technologies and challenges in lieu of Beresheet 2 program. First, to those of you who are coming from the aerospace system, when we deal purely with space, you have to forget about aerodynamics. No aerodynamics, no air, no lift, no drag. And the only physics that apply here the simple, very simple and basic mechanics law. First one is the equation, non-equation equation of the gravity forces between two masses. Everybody learned this in high school. The second equation is the momentum equation, which means that the force that we apply by the spacecraft thrusters multiplied by the time we apply this force is equal to the mass and multiplied by the delta V, or the delta velocity that is created by this force that act in on a time basis. Delta V, or the velocity, the variations in velocity. Delta V is a very known and usable term in space. And every mission that you start to plan, the question is, the first question that you ask yourself is how much delta V is needed for that mission. And this is the prime factor in which determines the size of the spacecraft and how many propellant or how many kilograms of propellant will be used in this mission. And the last equation here, the third one, is how we calculate this delta V. So delta V is proportional to gravitation and ISP, which is the specific pulse, or the let's say the energy that you can create from a propellant, and it's multiplied by Lan. The M0 is the initial weight, or the total weight of the system, divided by MF, which is the final weight of the system. So in terms of spacecraft, the M0 minus M5 is actually the propellant weight. So this is the way we compute or calculate for a specific delta V, how many propellant we need when we assume what will be the dry weight, let's say, of the spacecraft. So this is a very basic equation when you start your design. However, this equation, because it's a Lan type of mathematics equation, you can see how is the behavior of this function, and you see that in order to get performance in terms of delta V versus the mass ratio between the initial weight and the final weight, which means actually the propellant weight, you can see this behavior of this curve, which means that if you try to increase your system by weight or by propellant, you are getting less benefit in delta V or in performance, which means you have limits how much you can increase the system and still get performance, delta performance. Now, why I'm focusing on this, because the bottom line conclusion here is that you have to be very much concerned along the design with the weight of the system. So if you're trying to achieve more performance by increasing the weight, then you start to become inefficient because of the nature of this curve. So all those engineers who are, let's say, designing the size and the system, the conceptual design of the system, have to be aware of the fact that you have to maintain the weight very, very aggressively, unless you're paying a lot of penalty without getting too much performance. This is the bottom line conclusion of this very important slide. Another discipline that is very much different dealing with space is what we call flight dynamics. This is like the, let's say, substitute of aerodynamics in aviation, regular aviation. And here we have few components of flight dynamics. One component is the trajectory planning, which means how you leave Earth, how you do the route to the planning the route until the point you do the capturing with the moon, and how to do the exact maneuvering in order to be successful in capturing the moon. In this regard, we must say here that you have only one option or one match to do it. If you do it successfully, that's fine. If you fail to do this maneuver of capturing, leaving the gravity of Earth and being captured by the gravity of moon, if you failed on this, your system, your mission is over, because your spacecraft will go to the solar system, and you lose control of your spacecraft. So this is something that is very, very important. Flight dynamics. Another important discipline is the propulsion. You have to remember all the time, you don't have air, you don't have oxygen. If you need oxygen for your propulsion system, you have to bring the oxygen with you. Here you can see two methods of propulsion in deep space. So you're using, one of them is most popular, is using hypergolic fuel or chemical fuel. Here you can see in the example of Beresheet, we have 4 tanks here with 2 materials. One of them is 2 tanks are filled with hydrazine, and the other 2 tanks are filled with oxidizer. And when you mix together the hydrazine and the oxidizer in the thruster inlet, whether it's small thruster or big thruster, then you get a chemical reaction and you speed up the fuel, the components, and with high speed, and you get thrust. So this is the most popular way to do the propulsion, getting thrust. The other way that is used is using electrical propulsion. You can see here the way we do it. We have we use electricity. It's coming from the sun to the solar panels. And we have the propellant. The propellant is like some sort of gas like xenon or other type of gas. And you have, let's say, a system that convert those atoms of this gas to be ions that are accelerated by a magnetic field, electromagnetic field, and getting out of the spacecraft, as you can see on the right-hand side, getting out with high speed. And this energy is converted to thrust. However, the ability to get a high level of thrust is very, very limited. This thrust that you can extract from this system is measured by a part of a Newton, like half Newton, a quarter of Newton. So you need to apply some of redundant system in order to get few Newtons or maybe less of thrust. This kind of system is not effective when you have a landing to do, because during landing you have to develop high thrust to balance the weight of the system. even though the gravitation on the moon is like 1/6 of Earth, then still you have to apply a lot of trust in order to break the velocity of the spacecraft and the landers and break the gravitation acceleration. So you cannot do it with electrical propulsion. Electrical propulsion is good in order to travel between planets when you have a lot of time, a lot of months or few years to get from point to point. So even if you have a low thrust acting for a long time, you can speed up and get to far or deep space, far destinations, but you cannot do landing. When you have gravitation forces, and you cannot do fast braking of speed as you need during landing. So this kind of propulsion is very limited in the way it's implemented. Other discipline that's very interesting and very challenging is the flight control system. At all the time of the mission, we have to control the attitude of the spacecraft. We have to find the location to navigate and figure out the location and speed. We have to carefully design the capturing maneuver. We have to achieve orbit stability. We have to do the autonomous landing. It's all flight control. We have to use many different types of sensors like star trackers, IMU, sun sensors, reaction wheels in order to control the attitude. So we have to orchestrate all of these sensors and get to successful soft landing. So flight control is also a very complicated and important part of the effort here. Communication system is also challenging. We are talking about long distances. The moon is far away 1,000 times than the International Space Station. So the space station is located like 400 kilometers from Earth, and the moon is 1,000 times far than the space station. So we're talking about long distances. We have a very limited bandwidth we can transfer from that distance. We have latencies. We have a problem to maintain continuity because in the communication, because Earth is rotating, and so you don't have like line of sight with the spacecraft. So if you want to maintain line of sight, you have to use many antennas spread around the world, like worldwide antenna system. And in order to get valuable information, sometimes you have to use very large diameter antennas, could be between 30 to 70 meters in diameter. There's huge antennas, very expensive one. So you have to use this deep space network in order to carry the information from the spacecraft to Earth. This is also a very expensive process. Thermal control is also a big story here. In space, we don't have air, so we cannot remove heat by convection, not by conductivity. The only thing that works properly is radiation. So we have to use like OSR, special space radiations. We have to attach all the electronics close or behind those OSRs in order to convert the heat that is generated by electronics to those radiators and to move it to space. And we have to maintain also the temperatures of all the equipment, the fuel system, in the normal temperatures, while outside it's very, very, very cold. So in order to to make sure that your system will work all the way. It's a lot of analysis, of a lot of usage of thermal blankets, and also shields, and also thermistors, and only many devices to measure, control temperature. It's very complicated, and you have to seal your spacecraft and make it sustainable all the way in terms of temperatures. So you have to protect the equipment from the cold outside, and you have to get effective way to remove the heat that is generated by your electronics internally to move it outside. So you have here double challenges, and you have to make this to balance all the system all the way, all time. Structural design is also challenging. We have to carefully monitor the mass and the CG in order to be successful. We have to use special materials that are applicable for space. And you have to use manufacturing techniques for lightweight design and manufacturing, like additive materials, additive production, as you see here in one of the pictures, in order to get a lightweight structures with a very minimal weight. Avionics and electrical system is also a challenge here. We have to maintain the reliability of the system. There is a conflict here between weight and reliability, so we have to do these trade-offs all the time and decide how much reliability and redundancy we have to put in the system and still maintain a low weight. So this is a dilemma that we have to confront with. We have I think the biggest enemy of the electronics, avionics, is the radiation, the high radiation that is existing in space. So we have to protect the systems from radiation. There is also time effect on the system, because you continue to absorb radiation all time. And at one point of time, when you have too much radiation, your system can break up. So it's also something to consider. And we have to also to use solar panels in order to create the energy to your system and to make it very, very effective. Another challenge, of course, a big challenge, is the environmental condition. And here we have two very different challenges. The first challenge is during the launch period, the launch phase. We are dealing with very high G loads, around 10 Gs in the vector of the acceleration. We have shocks. We have tremendous vibrations in the payload bay of the launcher, and we have acoustic noise. And we have to make our system, the spacecraft, very durable and very much proved to these loads before we are able to get a permission to put it on a launcher. So this is one phase and one story. And the other story is the in-space environmental conditions, extreme temperatures, the radiation outside, the vacuum, microgravity, and other effects. These are all effects we have to consider, to control, and make sure that it's not hurting our system. Another challenge is, of course, the testing. And let's assume that we can never test our system completely to the space environment on Earth. So we can do many different type of testings, but you can never simulate all the environment in space on Earth and make sure that your system will be perfect for that. It means that you always have to expect for surprises, because you cannot test everything simultaneously on Earth. So we do a lot of vibration shock tests We do acoustic noise. We do thermal vacuum chambers to simulate temperatures in the vacuum. We do drop tests to make sure that your landing system is okay. We do radiation tests. Each test mostly is done separately, and we pray that all the tests that we do will be sufficient to avoid surprises in our journey to the deep space. But you always have to expect for surprises and hope to be able to overcome them all the way to your destiny. So this completes my presentation, the last chapter. So I'll stop the sharing now and get back to the discussion or questions about what you have seen so far.
Well, thank you very much, General Sarid. It was a wonderful talk, and especially the lesson is that we have dreams, but we are presented with reality, what we have to do to accomplish dreams. But this is a challenge. So the braves and determined will take up the challenge and realize the dreams. The others will stay and be just watchers and looking how the things are developing. We on the other side, and I'm the one to pursue this, that we take up challenge and we see how we can participate and see how we can do something about to realize the dreams. Okay, thank you very much. And so the questions, please, I don't know. It's, can you read the questions?
Okay. I see here some questions on the chat, so I'll try to answer them, okay? So the first question is, what are the design differences between Beresheet 1 and 2? What did you decide to change? Okay, you see that the mission of Beresheet 2 is not completely different, but quite different from Beresheet 1. But we actually using the same technologies that were developed in Beresheet 1. Of course, we have all the part of the mission that will do the release of the landers, two landers, and everything. So it induces more complication, more complexity to the design, of course. But generally speaking, we're using the building blocks and technologies mostly that were developed in Beresheet 1. Now, in addition to that, we have lessons learned from Beresheet 1. So in places that we find a need to change or to enhance the system or part of it, so we do a lot of improvements to the system, but still we're using the basic technologies of Beresheet 1. So this is the beauty of, I think, Beresheet 2, in which we utilize the investment done on Beresheet 1, but we are leveraging this to do a more complex and more inspiring mission. The second question, can you explain to us in more detail the technical characteristics of the propulsion system for landing on the surface of the moon? Okay, it's not only landing on the moon, it's not only the propulsion system. Propulsion system, of course, is very important and enabler to do so. And the challenge for the propulsion system is to break the speed of the spacecraft, of the lander. We are starting the landing process when the speed the horizontal speed of the lander is 1,700 meters per second, 1.7 kilometers per second. So this is a great, very high speed. So first we have to break this speed in order to start the sequence of descending to the moon. So in order to do so, we have to invert the spacecraft in a way that the thruster will be on the other side or on the opposite side of the vector of speed in order to apply the thrusters, full power, of course, in order to break this speed. And then once we breaking most of the horizontal speed, we start to break the vertical speed that is induced by the gravitation of the moon. Now, this process takes like between 15 to 20 minutes until soft landing. And the distance that the spacecraft is traveling along this way is about 700 kilometers. So from the point you giving the command to land until you hit the ground, or land on the ground, it takes like 700 kilometers, a way of 700 kilometers of traveling until you land. So you have to take this all in consideration when you determine where to land. Now, the real challenge in landing on the moon is not the propulsion, is the soft landing system in terms of flight control. After you break out the speed by the propulsion system, you have to maintain your spacecraft in the right attitude and the right speed to do hazard avoidance, not to land on a rock or something that will destroy your spacecraft. And you have to get to the ground in speed close to zero, vertical speed close to zero. And the sensors to do that and the algorithms how to do it and the control of the system is the #1 challenge in soft landing on the moon, not the propulsion, even though the propulsion is very, very important. Now, another question, was the problem from the wrong reading of the height by the altimeter or by the wrong calculation of the propellant in the landing phase? You're talking about, of course, Beresheet 1. No, this was not the problem. The problem is that we have a failure. We had a failure of IMU, Initial Measurement Unit. And during the last 10, 12 kilometers from the surface of the moon, and the ground crew decided to handle this failure by doing a reset to the IMU. And we had another IMU as a result. Well, we had redundancy in IMUs, but they decided to try to fix the problem with the IMU. The problem is that this command was wrong in a way that it's led to a reset to the main computer also. And during the reset of the main computer, the procedure is that the main computer is shutting down the engines until the reset is done. And this is something that we couldn't tolerate, being without the engines that has to break the speed to get the soft landing. So once we got back the engines power on, it was too late for the soft landing. We lost a lot of altitude and we didn't manage to break the speed. So it was a crash landing. So this is the sad story of Beresheet. And of course, we have to learn the lessons.
I presume that also the software that regulates the amount of propellant used for touchdown is also important. I mean, it must balance between the amount of fuel and the speed that goes down.
In this case of Beresheet, we didn't have a fuel problem. We had enough fuel to land, and more than that, the rules for the X-Prize competition was not only to land, but try to take off again and land on the second site, like 500 meters from the original landing site. It was a part of the competition, so we had a reserve fuel also for this maneuver called Hope. So propellant was not a problem for Beresheet 1. The IMU for failure was the prime reason, and the way that it impacted all the system.
Okay, thank you. Well, any more questions? I can't see. Well, if there are no more questions, I would like again to thank General Sarid for excellent talk and really review of the Beresheet 1 and general of the aim of Beresheet 2, but very importantly about technological challenges and the technological side of it, because that gives us the idea where and what has to be done about all this. It's lots of work, but with hope you can achieve. But I hope also with the help from us. Well, thank you very much, and we stay in touch and hope to see you sometime again soon. Either here in Croatia, I'll see you in Israel.
Thank you all for participating in this lecture. It was my pleasure to tell you the story, our story. I hope that it will inspire also your countries, your organization to make a brave steps forward, and wish you good luck and success in your journey to the space.
Yes.
So we'll be in touch. Yeah.
Okay.
Good. Thank you. Bye-bye.
Bye-bye.